Hello and welcome to Power System Analysis 2. We are in module 3.5. In this module, we'll be talking about the reliability of the power system and what is the concept of reliability in this optimal operation. Okay, now previously we have seen different kinds of optimal operation where the different units have been distributed different loads depending upon the load so that the fuel cost is maintained. Now, not only that, not only have to maintain the reduce the fuel cost, but you should also need to change the uh, uh, change the power supply depending on the reliability considerations. Okay. Now, what is reliability? You have to understand that it is not only the power should be transferred from the source to the load. Not only that, but it should have a constant power power supply. Okay, with a particular voltage and a particular frequency. So you need to have the system to be reliable that you can switch on your unit and go and do not think about whether the unit will get damaged when the power is when there is a low power or a high voltage or not. That means you are relying on the system that it will provide you with the best output. Okay, so this is a text taken from the book. Is with the increasing dependence of industry, agriculture, and day-to-day household comfort upon the community of electric supply, the reliability of power system has assumed a great importance. Every electric utility is normally under obligation to provide to its consumers a certain degree of continuity and quality of service, that is voltage and frequency, in a specified range. Therefore, economy and reliability, that is security, must be properly coordinated in arriving the operational unit commitment decision. So that is what the book says, that it is the reliability is the basically the security part, is that you cannot allow the voltage to fluctuate, not that we can allow the frequency to change. Okay, so we have to think of unit commitment but also keeping the reliability in mind. Okay, now in the reliability considerations, it is basically how purely economic UC, that is unit commitment, UC decision must be modified through the consideration of reliability. That is the reliability consideration, how we are modifying the UC decision depending on the reliability. So there are 2 points here. There are in order to check this reliability, we need to store some reserve. Okay, so one is to meet the load demand under contingency of failure, that is forced outage of generator or its derating caused by minor defect. It is the static reserve capacity that is required. So in case of any fault and the generator is taken out, there should be a static reserve that should be there, which during the outage of the generator, that can provide the power. And next is the spinning reserve. Now you have to understand what the spinning reserve. To meet the contingencies, the capacity of the unit online, that is running, they must have a definite margin over the load requirement at all times. That is spinning reserve. Basically, what it is the spinning reserve is nothing but keeping one of the generators on, one or more generators on, just like that. Okay, it is there because in order, if something happens, the generator can be switched to that other generator. Okay, so why it is done? Because let's say one generator is turned off or goes out of service, it take a long time of starting a new generator, and again there is a cost of the charge starting a new generator. So sometimes an extra generator, extra one or two generators are kept running at a no load, thinking that whether when these actually any generator outage will occur, the the load can be shifted from the current generator to the already spinning generator. That is called a spinning reserve. Okay, so either we have a static reserve or we have a spinning reserve. Now why are these? This to enhance the reliability. When the generator is disconnected, you'll have a power break. Okay, there will be no power into the load. That we cannot allow. Okay, we need to provide the consumer with a constant power with the same voltage and same frequency. So we cannot allow one unit to shut down and then again start. When it shut down due to some fault, there should be some backup. Okay, so the two types of backup that are there. We have a static reserve capacity and the spinning reserve. So let us take an example here. Okay, this is a random unit performance record neglecting the scheduled outages. So you take a random unit or a random generator, just so you see it is starting with a down state, that it is not started. Okay, so at a certain point it is started and it is called an up state, that is the generator is started, and then it is an uptime given by T1 or T1 up. Uptime is nothing but the time till the generator is working. Then certain failure occurs, okay, and we have a downtime. Okay, then there is a time for the repair. So after repair again you have a second uptime T2 up. Then again you have a downtime, and then you have a T3 uptime, and then again you have a downtime. Okay, so this is a up and down time. You can see there is no you cannot predict that for how long the generator will be up, and then when there will be a fault. So the up down and the downtime obviously will depend on situation to situation. Now in order to understand how good the condition of the generator is, you need to find some kind of parameter. Okay, so you need to find out the mean uptime. What is an average time the generator is up? So what you do, you sum all the uptimes and you divide by the number of cycles. Okay, so this is called the mean time, mean uptime. Now the mean repair time or downtime is again you sum up all the times the generator was down and divide by the number of cycles. So the mean cycle time is nothing but the time it was up plus the mean time it was down. The inverse of these times can be defined as rates. So you can say lambda as the failure rate and mu as the repair rate. So you can see 1 by capital T up is the failure rate, and 1 by capital T down is the repair rate. So you can say so with these different values we can judge the condition or quality of the generator. Okay, now there is also this probability of will the generator be up or the generator will be down. This probability is given by P. Okay, so probability of up is called the availability of the generator, and probability down is called the unavailability of the generator. Okay, so how these probabilities are being defined is given here. Okay, it is nothing but the fraction of the uh, total rates. Okay, so these tell you that how what is the condition of the generator again. So there are different parameters to define the generator conditions. Then we'll come to a certain concept called the pattern security function. Okay, so what is security? A breach of system security is defined as some intolerable or undesirable condition. Okay, so a system is secure, that means there is no problem. As then any kind of problem in the system, we say that cannot be tolerable or undesirable. We can say that the security is breached. So we have to we need to understand. We cannot say how strong the security is. These are vague terms. So if you say a person is good, a person is bad, those are very vague terms. In science and in engineering, we cannot depend on these. The generator is good. How good? So in order to get some kind of rating, we need some kind of parameters, and this pattern security function is one of those parameters. It is nothing but probability that available generation capacity, that is the sum of the capacities committed together at a particular hour, is less than the system load at that time. Okay, so what is the probability that the amount of generation is less than the system load? Okay, so that probability is called the pattern security function given by S. It is sigma of P and R of I. So P is probability of system being in the state I, and probability of system state I causes breach of the system security. Okay, so you have both probability of the without the breach and with the breach. Okay, so this is defined by the pattern security function. Then we'll talk about security constraint optimal unit commitment. So there is a term we have defined as maximum tolerable insecurity level, MTIL. So this MTIL is given by system management the MTIL for a given system is a management decision which is guided by past experience. If the value of S exceeds MTIL, the economic unit commitment schedule is modified by bringing the next most economical unit as per UC table. What happens now? The management of this power system company, they create some value of S. The S, that is the pattern's security function S, they have created that value, and they call it as MTL, that is maximum tolerable insecurity level. So they say that if S is this amount of value, we can tolerate it, so we are not going to be concerned with that, and we'll go on with our power supply. Okay, now if a certain place is when the value of S exceeds that MTIL value, then we can say now the system is insecure. Now this current unit commitment, what we have said that this generator 1 and generator 5 and generator 3 will run, that will not do. We'll check the next best unit commitment combination. Okay, So then it is shifted to the next best combination, and then S is then recalculated. The process is continued till S is less than MTIL. So this is one of the security measures. There again, there should be a startup consideration. Now, what is the startup consideration? Startup cost must be taken into consideration from the point of view of overall economy. We need to check that to start up a generator, there is a cost involved. I have told you previously. So we must therefore examine whether or not it will be more economical to avoid one restarting or by continuing to run the unit in the period. So that should be a consideration, that whether we keep the generator running without any load, or don't need to stop the generator and start it later, because there is a huge starting cost. Okay, so this is the end of this lecture. In the next lecture we'll look at a different topic. Okay, for now, thank you so much.